Hey, so we're going to look at bonding before we look at naming. So everything is all about bonding in chemistry. Ionic bonding, we've got covalent bonding, we've got metallic bonding, and it's what the electrons are doing. Up until this point, we've been talking about the atom, and then we started focusing on what the electrons were doing. Now we're really focusing on those outer electrons and what they're doing, because that is chemistry. So we're going to begin by looking at ionic and then covalent. We won't be looking at metallic, but we're just mentioning it because it is a type of bonding that you need to be aware exists. It won't be on a test or anything, but you may have it in future chemistry courses. So ionic bonding. Right here, what you're going to have is an element that has an electron on the outside section in the valence area. And for whatever reason, he's only got one electron. He's kind of happy to share it, to give it away if someone comes along. So something's going to be motivating that electron to leave the atom. And it's probably someone nearby that really wishes he had just one more electron. Right now, this one has 7. He's almost got 8. And probably something nearby is offering some energy money over there to the sodium to give up some of its electron. It's one electron. So they don't just like leave randomly and float around. They have a reason to leave. So I guess nearby, this electron gets moved to the chlorine. When that happens, remember when something loses electrons and becomes positive, it's called a cation. And remember that they get smaller. That's from section 2. And then remember when you gain an electron, that becomes an anion and it's bigger than its original neutral state. So then when they come together, you know this, positives and negatives attract. So that's what's happening. The positive is attracted to the negative. In chemistry, instead of saying positives and negatives attract, we call it a Coulombic attraction. And this is governed by 3 things. Like there are 3 things that make a Coulombic attraction stronger, 2 things that make it stronger. One of them is how much charge, and so more charge basically. More charge means more interaction. Attraction. And then the second one, it has to do with the size. And so right now, like imagine here's a chlorine and he's got this negative charge. If we had an atom that was a lot larger and just had the negative charge, see, you can kind of see that it's spread out a little more, maybe a little diluted when you're thinking of it over the surface, the whole atom. That's kind of sort of what happens. So in fact, a smaller size gives better attraction. And these will combine in your smallest ratio possible. And that's how we talk about them, is that smallest ratio. We call this a formula unit. And kind of like with atoms, this little grouping, this little pairing, they're stuck together. 6.022 times 10 to the 23rd. Yes, we do abbreviate this with an F and a U, equals 1 mole. That still applies. So you learned that in Module 2, and it still applies. So the interesting thing about this, though, is that these atoms, it doesn't just have to be sodium chlorine. I'm going to scroll up to the periodic chart up here. So anything in the red combining with anything in the blue. So if you kind of get used to this look on the chart, as long as you've got something on the left side of the stair steps, so something on the left and something on the right, you're looking at an ionic bond. Or something in the red and something with a polyatomic ion. So lastly, these are interesting how they look. When they get together, they don't just stay as little formula units, but they get just the tiniest bit of attraction to the one next to it and to the one next to it. But you can see overall it kind of has this cube look to it. We have different categorizations for the different cubes. You might see those later also in chemistry, but not in this course. But you've got the positive and the negative, but notice that the negative one on the next formula unit is what gets next to this positive charge. And again, this negative one is going to go over there. So they kind of line up all spaced perfectly, alternating in positives and negatives. Sometimes it's not positive, negative, positive, negative. Sometimes it's positive that has a 2 plus. So you can have like a 2 plus, and then you can have negatives on it also. So these different shapes will look different and unique but they group up like that. And one of the consequences of this is that they have some different properties than some of the other bonding types. One is that they tend to be solids. Another way we say that is that it has a high melting point. That just means like if it melts at 100 degrees Celsius and you put it on a hot beach day, it is not going to melt. It's going to be a solid, because there's no way that 1,000 degrees Celsius is going to be melting on a hot day at the beach. Some of the other things is that they do tend to dissolve in water. They don't all dissolve exactly the same way in water, but they will dissolve somewhat to a lot in water. Once they've done that, they will conduct electricity. This is kind of a big, we like to focus on whether or not something will conduct electricity or not. So once in the solid form, they don't conduct electricity. But we make a big deal about this because in water, this is a big deal. This is the reason why your water conducts electricity, and you need to be careful with electricity in water. It's because when you dissolve ionic solids in water and your tap water has ionic solids dissolved in it, it will conduct electricity. And just keep in mind that we won't ask you to draw this shape, just showing you kind of what it looks like. We're only going to be asking you to put these in groups of their smallest ratio. NaCl, not Na2Cl2. And that is the ionic bond.